This is Mrs. O'Neill for AP Chemistry, Chapter 5, Section 4, Enthalpies of Reaction. You should have watched the intro lesson on endothermic and exothermic reactions. Here are my notes. I'm going to go through these kind of quickly because you should know most of this information already. This is just more review and understanding systems versus surroundings. So you know that thermo means heat. Of course, endo means that heat is entering the system or the process, and exo means that the heat is being released into the surroundings. So an exothermic reaction, heat is released from the reaction or process or system to the surroundings, and an endo is that reaction, process, or system taking in or absorbing that heat from the surroundings. So that's what I want you to hopefully understand from this video is there's a difference between the system, which is the actual system is actually the reaction that's occurring or the process that's occurring. That's the system. The surroundings is everything going to be around it. And of course, the universe is all of it. It encompasses the system and the surroundings as a whole. Gave you a nice little flow chart as he always does. He went over that exothermic reaction energy diagram, which in section 5.2.2, you should already have this in your notes. And the same thing with an endothermic reaction energy diagram. So how do we measure exo and endo? Well, we do it with a thermometer like we normally do. However, we need to remember that in this example he gave us, we're measuring the temperature of the water, which would be the surroundings. When we put that salt into the water and let it dissolve, the temperature of the water, the surroundings went down. So since the temperature of the surroundings went down, the actual system or the process or the reaction that took place is endothermic, because that process, that system, needed to absorb that heat energy from the surrounding water in order to get cold. So to your notes packet, and in this section, you're going to understand this quantity of enthalpy is directly proportional to the amount of reactant consumed in the reaction. Pause the video, read as you write those blanks in, and then play to hear my words. So again, just reminding you, we can measure the enthalpy of the surroundings, but we cannot directly measure the enthalpy of that system or that process or the reaction that's occurring. So we want to remember the Q of the surroundings, and Q is that heat, equals the negative Q of the system. So the magnitude is going to be the same. It's just the sign that changes. Now this Q is actually going to become enthalpy. It's going to become delta H. So we measure the Q of the surroundings. This is going to equal the negative Q of the system. Okay, or again, that Q is also the same as delta H, enthalpy. So read this over, making sure you're understanding, again, giving you a visual of here's our system and energy is going into the system. That system is gaining or absorbing that energy, and we're going to give that system a positive Q or a positive delta H. We're an exothermic reaction. Again, read over that. Hopefully this makes sense to you that that system is going to release that heat energy into the surroundings, causing it to be a negative Q or a negative delta H. So there are different types of systems, and what I would do is play the video as well as the next few slides where I give you examples, and then maybe go back and draw what you want. So in a system or surroundings or a universe where it's it's called an isolated system, there's no exchange of matter and no exchange of heat. So the system and the surroundings are at exactly the same temperature, and it's kind of like in a box. Nothing's getting in, nothing's getting out, and there's no exchange of heat. However, in a closed system, if the system and the surroundings have a different or at different temperatures, we know that that heat can be exchanged. However, matter cannot be exchanged. So in a closed system, we can release heat or gain heat, but we cannot exchange matter. In an open system, there can be exchange of matter and an exchange of heat. So in an open system, heat can be gained or lost, and the matter can also be gained or lost. So here's some examples. In a calorimeter, which you already learned, It's an isolated system. So we have our little sample of, let's say, a carrot, and we have it connected to an ignition box, and that carrot is submerged. It's a closed system, and it's submerged in water, and that water is also in an isolated calorimeter. So we're going to ignite the box, we're going to burn that piece of carrot, and it's going to release some heat energy. Now, the carrot, there's nowhere for it to go, right? Even though it's burnt, it's nowhere to go. Matter stays enclosed, as well as the water and that temperature that we measure the temperature, but that water, nothing gets in and nothing gets out. And even the heat gained or lost, nothing gets in and nothing gets out, because again, it's in an isolated system. On the other hand, in a closed system, okay, we have an example of equilibrium vapor pressure. And we talked a little bit about vapor pressure in class, but we want to remember that the water molecules here, let's say, are going to evaporate, and at some point there's too many of them, so they're going to start condensating. And when that rate of evaporation and condensation are at equilibrium with each other, or at equal rates, then we can call that vapor pressure. And evaporation obviously is an open system. We have some water in a test tube, and that water eventually is going to evaporate into the air or the surroundings. Here's some information about evaporation and vaporization. So I would pause and read that over, because there is a difference, even though we kind of use those two words interchangeably. So enthalpy change of a reaction is a simple equation, H of our products minus H of our reactants. So we're going to take the total amount of energy that our products have minus the total amount of energy, heat energy, that is, of our reactants. So positive delta H is an endothermic, because the system is gaining that energy, and in an exothermic are negative delta H, because that system is losing energy. So one way you're going to see me remind you of this information is in class, when I give myself a hug and kind of cross my arms like this little boy is doing, okay? He's kind of giving himself a hug and crossing his arms. He's gaining that heat energy and making that plus sign, versus when we have an exothermic reaction, you're going to see me spread my arms apart, because I'm releasing heat out into the surroundings. So if I'm the system, or this lady's the system, she's going to make her arms go straight across like a negative sign, because the system is losing energy, giving it to the surroundings. So again, look this over. Hopefully this makes sense. How do we have a delta H positive? Well, if we take our product number, which there's a lot more energy here than our reactant, we're going to get a positive delta H. And we want to remember that that system is gaining energy, right? When we're breaking those bonds, when we're going up that hill. Same thing here. When heat is leaving the system, we have products here have less energy than the reactants. So what's happening here is, right, we already have a small number minus a big number, and we get a negative. And again, just reminding you that when we're coming down the hill, that system is losing energy. So again, those graphs that you should have watched that video 5.2.2 and put them into your notes is going to be very important from here on throughout the course. Just a little fun here. See what Sam and Julie are up to in chemistry. Teacher gave me salt A. Ooh, and I have salt B. I'm supposed to add 5 tablespoons of salt A to this flask of water. I'm doing the same with salt B. Brr, this flask is so cold. Woo, this one's hot. So another way to remember, again, I'm just going to give you a couple more examples. Going up steps takes a heck of a lot more energy than going down. So again, we have endothermic going up, exothermic going down. Just like in education, as you move up the chain, or even in some kind of business world, when you're moving up the ranks, your position changes. That takes energy going up the steps, going up in education. It's a little bit easier coming down. This one's a little harder to understand, but hopefully this gives you a better visual. As we go from a solid to a liquid to a gas, we are gaining energy. And because we're gaining energy, that is endothermic. Why is that endothermic? Because those molecules are separating. So the solid molecules or atoms need to absorb heat energy in order to go to a liquid. The liquid needs to absorb energy to go to a gas. So obviously the opposite is true. So when the molecules go from a gas to a liquid, liquid to solid, they're becoming closer together, and heat is released into the surroundings. So I always like to say, think of heat as a substance in a reaction. If the reaction is endothermic, I'm going to put heat as a reactant. And if the reaction is exothermic, I'm going to put heat as a product. And this is really going to help you when we're doing stoichiometry problems as well as equilibrium problems later on. So here's an example. If I have a negative delta H, I know the reaction is exothermic. Boom, I'm going to put heat as a product. And I'll go over that example over and over and over again. So why is it exothermic? Well, we know that when we take hydrogen and oxygen to form water, heat is going to be released into the air. And if we look at our energy diagram here, right, our products have less energy than our reactants, and we're going to have a negative delta H. So pause the video, read this over, see if you can come up with an answer, and then see if you get it right. Hopefully that makes sense. So there are three characteristics of enthalpy changes. The first one is extensive property. Extensive means that it's going to depend on the amount of material. The amount of material, or that magnitude, is directly proportional to the amount of reactant consumed in the process. And you might want to read this over as well. That's something extra. So here's an example of an extensive property. Here's our reaction. Our delta H is negative 802. Uh-oh, what did I do to this equation? And now the delta H is negative 1604. Well, I doubled the reaction, so the quantity, the value of my delta H also doubles, but the sign stayed the same. So keep in mind that when you double a reaction, you can also reduce a reaction. So sometimes instead of doubling a reaction in the future, we're going to have to reduce the reaction. So then we will reduce the delta H. So reverse reactions, this should kind of make sense when we talk about the Q equals negative Q of the systems versus surroundings. Here we have an example reaction. Its value is negative 802. I reverse the reaction, so it's the same exact reaction, just in reverse. My products became reactants, and now I have the same value, but my sign changed. I went from an exothermic reaction to an endothermic reaction. The state of substance also is very dependent on delta H. Well, let's look at this. We have that same reaction again, and now instead of forming gas water, we formed liquid water, and now our delta H of this reaction is going to be different. Well, why? Well, the process of going from H2O gas to H2O liquid also takes heat energy. So that amount of heat energy has to be reflected in the overall reaction. We want to remember that delta H is going to be a conversion, and we're going to use this delta H as a conversion, but instead of per 1 mole, the delta H of a reaction is really the amount of moles related to the coefficients of that substance in a balanced equation. So let's do some problems here. So we're going to talk about delta H here and the stoichiometry of it. So example 1, read that over, then pause. Now, hopefully you read that. And the first thing I like to do is put what they give us. They give us 5 grams of the oxygen, and they want us to know how many kilojoules of heat is going to be released. Now, just as a reminder, this guy, negative 566 kilojoules, since it's the delta H of the whole reaction, that means negative 566 kilojoules is going to be released when 1 mole of C3H8 or 5 moles of oxygen, okay? And 3 moles of carbon dioxide is being formed, and 4 moles of the water is formed. So I'm going to start with what they give us. I'm going to go from grams to moles. Now I'm going to use that delta H conversion, negative 566 kilojoules per 5 moles of oxygen, since that's what I want. And then, of course, do the math and get negative 17.7. Example 2. Again, look that over, see if you can do it, but I believe I have one more that I want you to try on your own. But let's look at this. So again, the negative 1107 kilojoules is for the whole reaction. So 2 barium, 1 oxygen, and 2 barium oxide. So the first thing I do is put the information they give. I'm going to start with grams of barium. You should know you're going to go right to moles, but now we're going to use this kilojoules, the delta H conversion, and we're going to say for negative 1107 kilojoules per 2 moles of the barium, since that's what I'm interested in, to get the negative 23.2 kilojoules. All right, Your turn. Give it a try. I'm giving you the value of positive. I'm giving you the 5.10 grams of hydrogen. So how many kilojoules of heat are consumed? Again, because we're dealing with a product this time. So again, I put the information down underneath the equation. That you should definitely have gotten. Okay, so again, it's going to be positive this time, 128.1 per 2 moles. And there's your answer. All right, see you in class.